Let's get started. Haber-Bosch process, which also known as Haber ammonia process or synthetic ammonia process. Haber-Bosch process is invented by two well-known chemists. So the first one is Fritz Haber, a German physical chemist who won the Nobel Prize for Chemistry in 1918, and the second one is Carl Bosch, a German industrial chemist who also won the Nobel Prize for Chemistry in 1931. Haber-Bosch process is a method of directly synthesizing ammonia from hydrogen and nitrogen. It directly combines nitrogen from the air and hydrogen under extremely high pressure and moderately high temperature. This process was the first industrial chemical process to use high pressure for chemical reaction. This process also made the manufacture of ammonia to be economically feasible. So I have attached a picture which shows how Haber-Bosch process works. So this is the chemical reaction that we can derive from the process. The process is a reversible reaction, and there are three conditions, which is iron as catalyst, and the temperature must be between 450 to 500 degrees Celsius, and the pressure must be in between 150 to 200 atmosphere.
Hello there. I could see that you have already finished from the Hadith part, which is the introduction of the Haber-Bosch process. And then before I start my presentation, I'd like to wish to all my Muslim friends a happy Eid Mubarak. And then, without wasting our time left, I would like to give a presentation about the methane steam reforming and the methanol synthesis. Okay, based on the slide here, we have got the methane plus with water, and then we could get the carbon monoxide and the hydrogen gas. And then there are several conditions we must obey in order to do this experiment. And then we have to get the temperature around 1273 Kelvin. And then we could also use the nickel as a catalyst to speed up the reaction. And then the enthalpy of reaction is 200 kilojoule per mole. And then based on this enthalpy, we could see that the reaction is an endothermic reaction, and it is absorbing the heat or the energy from the environment. Then we have got the methanol synthesis, and then this is the equation. The carbon monoxide plus with the hydrogen, we could get the methanol, and the enthalpy of the formation is a negative 91 kilojoule per mole. And based on this enthalpy, we could see that the reaction is an exothermic reaction, and it is releasing the energy to the environment. So there are several conditions for this experiment to occur. So the first one is the temperature must be around 200 to 300 degrees Celsius, and the pressure must be around 10 megapascal. And to speed up this reaction, we could also use the copper oxide or zinc oxide to lower the energy activation. So I think that's all from me. There are some more information that I had left on the slide that you can read. Thank you.
Hello, now we'll talk about the chemical equilibrium concept in this question. What is chemical equilibrium? Chemical equilibrium is a condition during a reversible chemical reaction in which no net change in the amount of reactant and products occur. So I will move to the reforming process, which is CH4 plus 2H2O will form CO plus 3H2. So this enthalpy reaction is about 205.896 kJ per mole, and it's an endothermic reaction. Therefore, the equilibrium position will shift to the left. Next, about the same gas reaction, which is CO plus 2H2 will form CH2OH, and the enthalpy of reaction for this reaction is negative 128.571 kJ per mole, and it is an exothermic reaction. So the equilibrium position will shift to the right. Lastly, about the Haber process. Haber process is N2 plus 3H2 will form 2NH2, and the enthalpy of reaction is negative 92 kJ per mole, and it is an exothermic reaction. Therefore, the equilibrium position will shift to the right.
Oh, hello everyone. Now we will see the molecular geometry of each molecule that involved in this reaction. So first of all, we have N2, that is nitrogen gas. So to start off, we have leaf structure here. So based on our leaf structure, we have triple bond and 2 lone pairs. We can really see the only geometry that is possible here is just a straight line, which means it has linear shape with an angle 180 degrees between the bonds. Next, we have ammonia, which is NH3. First, look at the leaf structure. We want to visualize those 3 hydrogen and the lone pairs above the nitrogens. So, based on this, the shape of NH3 is trigonal pyramidal with an angle 107 degree. For hydrogen gas, this is the leaf structure for H2 and it is in a straight line, so the molecule geometry is linear with angle 180 degree. I'm sorry, I just drink my water because next, we will see the molecular geometry of H2O, which is known as water. We have 2 lone pairs and the 4 steric numbers. So, we have a band molecular geometry for water. We can see that the bond angle is 109.5 degree. So, let's move on to this H4. Methane has the steric number of 4 and we don't have any lone pair. So, we have the tetrahedral shape and the bond angle for CH4 is gonna be 109.5. Let's take a look at the molecular geometry for CH2OH. That is methanol. So we start with our Lewis structure. The central atom is the carbon. By looking at this, it gives us 4 steric numbers and there are 0 lone pairs, so it gives us tetrahedral shape with the angle 109.5. The last one, which is carbon monoxide, it has triple bond, same with nitrogen, so it gives us straight line. So the shape is linear with the angle 180 degree. So that's all the molecular geometry that involved in this reaction. Let's move on to the next person.
Now, let's continue with the calculation of enthalpy for all 3 reactions. First, let's begin with the reforming reaction. And as you can see in the table, we have the enthalpy of formation for all compounds involved in the reaction. And first, we have to write the balance equation for the reaction, which is CH4 plus H2O will produce 3H2 plus CO. Using the formula of sum of the reforming enthalpy is equal to the sum of product enthalpy minus the sum of the reactant enthalpy, we will get this working. And we will have the value of the enthalpy for the reforming reaction as 205.896 kJ per mole. And this reaction is an endothermic reaction since the value of Now, we shall continue with the calculation of the enthalpy of the synthesis gas. As you can see again in the table, we have the enthalpy of formation for the compound involved in the reaction. And now, we have to write the balance equation for the reaction, which is this. CO plus 2H2 will produce the methanol. And again, using the same formula, the sum of the reforming enthalpy is equal to the sum of the product enthalpy minus the sum of the reactant enthalpy. Here is the working, and we have the value of the enthalpy as negative 128.57 kJ per mole. And this reaction is exothermic as the value of enthalpy is negative. And here we have the shape of the graph of an exothermic reaction. Finally, let's continue with the calculation of enthalpy for the Haber process, which is the most interesting process in my opinion because it involves natural gases such as hydrogen and nitrogen. As you can see in the table, the enthalpy of formation of hydrogen and nitrogen is actually 0, and as for ammonia, it is negative 46. Now let's write the balance equation for the reaction, which is 1/2 nitrogen plus 3/2 hydrogen will produce ammonia. And as we multiply the equation by 2, we will get 1 mole of nitrogen react with 3 moles of hydrogen, will produce 2 moles of ammonia, with the enthalpy of negative 46.0, which will be times by 2, and the new enthalpy will be negative 92.0 kJ per mole. As we reverse the above equation and the whole reaction, we will get the value of enthalpy also be reversed from negative to positive, so the new enthalpy will be positive 92.0 kJ per mole. As the forward reaction is exothermic, we will have the reverse reaction as endothermic, and we'll get the enthalpy change for the reaction of the reverse reaction is 92.0 kJ per mole. That will be all from our group. I hope you enjoyed our video, and this is not the last time that you will see us.